Hey guys, Mrs. Young here. Time to go over our Chapter 7, the Solar System Study Guide for our upcoming test. So you are going to need to know the order of the planets of the solar system starting from the sun. So they are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. My very excellent mother just served us nachos. So remembering that first four, those are the terrestrial planets, those are the rocky planets, and the last four are our gas giants. The sun makes up 99% of the mass of our solar system, which is absolutely amazing to think about, that all of these planets and asteroids and comets and moons and everything that we learned about makes up just 1% of our entire solar system. That goes to show you how absolutely massive our sun is. What is an astronomical unit? The astronomical unit is the average distance from the sun to Earth, about 150 million kilometers. Because remember, if we are not thinking about AUs, we're dealing with extremely large numbers. And that is very difficult when you're trying to compare distances if you have these very, very large numbers. But if you have an AU of like Jupiter's AU is 5.2. And we have got Mars's AU at 1.5. And we have Uranus's AU at 19.2. So it's a lot easier to compare these numbers and just think about these smaller numbers, but keeping in mind that each of these is 5.2 times 150 million, 1.5 times 150 million. So what that is saying is that a planet like Jupiter with an AU of 5.2 is 5 times farther away from the sun than Earth. And Uranus at 19.2 is 19 times farther away from the sun than Earth. Okay. In the 1500s, Kepler discovered that the shape of the planet's orbit is an ellipse. It's nearly circular. It's not perfectly circular. The two factors that keep a planet in orbit around the sun are gravity and inertia. We'll talk about that question a little bit later when we have a graphic to look at. Describe the difference between a period of rotation and a period of revolution. Well, we've had this idea of rotation and revolution now a couple of chapters. The period of rotation is the time it takes an object to make one rotation or one spin on its axis. I didn't do that very good, did I? One rotation or one spin on its axis. So for us, that rotation, that one time on our axis is 24 hours or 1 day. And each of our planets in our solar system have a different length of rotation compared to Earth. Like Venus spins very slowly. Jupiter spins very quickly. So then the period of revolution is the time that it takes an object to make one all the way around the sun. So for us, that's 1 year, 365 and a quarter days. But the closer planets, like Mercury and Venus, they have a shorter period of revolution, so it's going to be less than 1 year because they're closer to the sun. And then we have our planets way out to like Neptune that take like 160 years to have one all the way around the sun. So they're the planets, the different planets that we studied this chapter, they're going to have a different period of rotation and revolution compared to that of Earth. The inner planets are known as terrestrial planets. They have a solid outer layer, so they are rocky. You can actually stand on them. Okay. My very excellent mother, terrestrial planets, solid outer layer, rocky. Okay, so then we are going to be looking at the different atmospheres. Mercury, it does not have an atmosphere, and the reason why is because it is not large enough to be able to hold onto those gases. Very extreme temperature range from very, very hot to very, very cold, no water. Even though Mercury is closer to the sun than Venus, it is not the hottest planet. Venus is the hottest planet. 460 degrees Celsius. And that is due to this greenhouse effect that we've got going on here with the atmosphere. Carbon dioxide, ooh, that's not a good one. Carbon dioxide trapping those gases, trapping the CO2 gases like a blanket and trapping them all in there and creating a very, very hot environment. So the atmosphere of Venus is carbon dioxide. Water, vapor and gases is what is our atmosphere. So we're like 79% nitrogen, 21% oxygen, and then like 1% trace gas for our atmosphere. We have a moderate temperature range, and yes, we do have liquid water. So as far as Mercury and Venus, nope, no water. Way too hot. Okay, we've got Mars, who also has a carbon dioxide atmosphere, not as extreme when it comes to its temperature ranges, and it does have water. It would be in a solid form. Maybe in our poles they have frozen water. So that is one of the areas they're looking at for could a possible second planet to live on, because does it have water? Check. Does it have an organic molecules? Haven't found that yet. So moving on to the outer planets. They're known as the gas giants. Outer planets are mostly composed of hydrogen and helium, which are the two gases that the sun is composed of. The hydrogen and helium, that nuclear fusion releasing all of that energy. So with Jupiter, we've got 90% hydrogen, 10% helium, lots of moons, rings and clouds, and they have liquid nitrogen as our center core. So Saturn, also the same atmosphere, 90% hydrogen, 10% helium, also a lot of moons, 60, also have rings, but have these beautiful rings, and there's horizontal bands of clouds, liquid hydrogen also in the center. We have Uranus, has hydrogen, helium, and with this one, we've added the gas of methane to both of these two. So that's what's going to give it its bluish color, is the additional presence of the methane gas. It has moons, 27, once again, has rings, and it has an inner core that is water and ice. Neptune, same atmosphere as Uranus, not as many moons, once again, rings, and water and ice for its inner core. So bottom line with this, which I want you to remember from here, is that all of the outer planets, they all have a ring system. Many times we think that Saturn is the only one that has rings, but they all do. They just might be very, very faint. And they all have moons. And they all have hydrogen and helium in their atmosphere. There's a lot of similarities between the outer planets as well. So we've got this graphic where we're going to be looking at describe how gravity and inertia work together to keep Earth in orbit around the sun. Well, it's absolutely a necessity that we have both of these in check, or else we would not be in orbit around the sun. So the gravitational pull of the sun is always toward the sun. So the sun is always pulling us towards it. It's not pushing us away. It is pulling the Earth or the moon if we're going around us. But that gravitational pull, the gravitational pull of the larger object is pulling the smaller object towards it. So the gravitational pull of the sun always is toward the sun due to the sun's large mass. So that's the gravity portion. Inertia, we learned about in first semester or so, is Newton's law of inertia that says an object in motion is going to stay in motion An object at rest is going to stay at rest. But in this case, an object in motion is going to stay in motion, and it wants to move in a straight line unless acted on by an outside force. Well, that outside force that's keeping us from moving in a straight line is gravity. So inertia is defined as the tendency of objects to keep moving in a straight line at a constant velocity. Remember, velocity, speed, and direction. The planet would move in a straight line without the sun's gravitational pull. The planet would continue out into space without the pull of the sun's gravity. So both of these working together. So it is both gravity and inertia working in tandem to keep us in orbit around the sun, or the moon in orbit around us. Name the 5 dwarf planets: Eris, Makemake, Hawaii, Pluto, and Ceres. Ceres is the one that lives in the asteroid belt, but all the other ones are located in the Kuiper belt. Remember that asteroid belt is between the last rocky planet and the first gas planet. So it is going to be between Mars and Jupiter is this asteroid belt. And our Kuiper belt is going to be extending after Neptune to 50 AU. So Neptune's AU is 30. So between 30 AUs, which is the outside of Neptune, extending out to a total of 50 AUs, is where we're going to have this Kuiper belt. And we're going to have a lot going on in that Kuiper belt. 4 of the dwarf planets live there. Name the 3 requirements for an object to be considered a planet. Well, it needs to orbit the sun. It needs to have enough mass to have a nearly spherical shape. So it has to be have enough mass to keep it, or to draw it in, enough gravitational pull and enough mass to form it into a spherical shape. And it also has to have a mass larger than the total mass of everything else around it. And also another one that we talked about, right, is that it clears its orbit. So this idea of a dwarf planet, they're going to meet some of these requirements. So our dwarf planet, it is going to orbit the sun, and it is going to be nearly spherical in shape. But it is with this one here and this one here that a dwarf planet no longer meets requirements for a planet, because the dwarf planet its mass will not be larger than the total mass of everything else around it, or it might not have cleared its own orbit. So that's how a dwarf planet is different than a regular planet. What is the difference between a meteor, meteorite, and a meteoroid? Well, bottom line with this one is that it has everything to do with where it is. All right, so if it is just out in space, just moving through space, then it's going to be a meteoroid. It's just out there. It's just doing its own thing, moving through the asteroid belt, perhaps. But if this same small rocky particle that's moving through space, if it suddenly enters Earth's atmosphere, it's going to burn up because of the thermosphere, one of the layers in our atmosphere, and it's going to produce this streak of light. And it is the friction in the atmosphere that makes that meteoroid, and the air around it so hot is going to cause it to glow. So then it's going to be that streak of light. People will sometimes call that a shooting star. And then the third one, if it makes it all the way through our atmosphere without burning up, and it actually hits the ground, then it is a meteorite. So a meteorite is going to be that meteoroid that strikes a planet. So to recap, we've got these small rocky particles, these rocks, this space junk moving through space. As long as it stays in space, We call it a meteoroid. Soon as it enters Earth's atmosphere, and the friction between our atmosphere and that producing it to glow, burning it up, then it is called a meteor. If it makes it all the way through and hits the ground of our planet or a moon, then it is a meteorite. So it has to everything to do with where it is. So I'm going to go ahead and stop this video and we'll pick it up with the next one. See you soon.